By request, this is the A-Level Physics, Paper 1 from 2017 by AQA. So, we have potassium 40, and it's used to date rocks. The isotope will decay into argon by electron capture. Here's the equation. Fill in the blanks. Well, really easy for the first part. 40 and 18. Just adding up the numbers. Really, conservation. And electron capture involves an electron neutrino. Okay. That electron neutrino is what carries away all of the decay energy. So what fundamental interaction is responsible for this decay? And explain which. So it's not just state which, it's explain which. Well, this decay is governed by the weak force. Okay, and the reason that it's governed by the weak force is that we have, essentially, if you really look at what's going on, you've got a proton and an electron, and we end up with a neutron and a neutrino. Hadron, hadron, lepton, lepton. Leptons are not affected by the strong force. They are only affected by the weak force and the electromagnetic force, and technically gravity, but such a small amount doesn't really matter. But it's definitely not affected by the strong force. So, because it involves hadrons and leptons, you can even have the fact that really what's happening is you've got up, up, down. So, and actually it's an up quark plus an electron to a down quark and the electron neutrino. So because the quark is changing flavor, you end up with, it just has to be a weak force interaction in order for that to happen. Okay, so 1.3, one decay mechanism for the decay of potassium 40 results in the argon nucleus having excess energy of 1.46 mega electron volts. It loses this energy by emitting a single gamma photon. Calculate the wavelength of that photon. Energy equals HF, which equals H C over lambda. So lambda is equal to HC divided by E. Okay, so go to the trusty formula sheet. So H is 6.63 times 10 to the minus 34 times C, which is 3 times 10 to the 8. It's actually 3.000 on the formula sheet. So we still got 3 significant figures everywhere. Okay. My energy, 1.46 times 10 to the 6. But that's in mega electron volts, so I have to multiply it by 1.6 times 10 to the minus 19 to get it to joules. Alright, calculator time. So 6.63, 10 to the minus 34 times 3 There's the 8 divided by 1.46, right? 1.46 to the power of, or times 10 to the 6, and 1 point, oops, not 16, 0.6, 19. There we go. So that's 8.52 times 10 to the minus 13. To the minus 13, and that's to my mind, that's a reasonable answer for a wavelength of a gamma photon. And the Mark Scream agrees. So, potassium isotope can decay by a second decay process to form a calcium nuclide, calcium-40. Suggest how the emission from a nucleus of a decaying potassium can be used to confirm which decay process is occurring. Okay, well, for this, what you have is 40, 19. Okay, and that is going to be 40, 20 calcium plus an electron and an anti-electron neutrino. So, well, I mean, so you can have essentially a detector, like a pair of detectors. Okay, so if you have a gamma camera or a gamma detector, to check for electron capture. I don't know if I like that or not, because it only says here, it doesn't say that every time you're getting a gamma photon, and with this you'd probably still have gamma decay, but you could definitely have something to detect the electron. So actually, I'm going to get rid of the pair of detectors thing, that, because I'm not going to worry about the first one. What I'm going to be worried about is detecting the electron. So so if you were to put this in a cloud chamber, if you had the first decay, which was electron capture, you would see nothing. Okay, because neither the neutrino nor the gamma photon given off is going to activate the cloud chamber, because they won't interact and they won't ionize the gas in the cloud chamber, whereas the electron, the beta particle, will. You'll see a long streak coming off of it. Okay. So there's no photon. You've got an antineutrino. That's what gets released. You can't really detect these things, right? You can't detect the absence of a photon being released, and you definitely can't detect an antineutrino being released. Because even the way the neutrino detectors work, they're huge, and they have to, one in, a trillion neutrinos is probably a high percentage of neutrinos to actually detect. Okay. Yeah, so that's the big thing that we want to see. All right, that is question 1.